see one more example of where the Bayesian answers disagree quite a bit. So we'll do one example of that. This is a fairly striking one. But then I want to show you a place where they do agree, which is in finite dimensional models, large samples. We'll talk about the asymptotic theory of theory of distributions. And in that case, we get a kind of agreement between Bayes and frequentist. So let's start with this example. It's not in the notes. And it's actually a pretty interesting example, especially because it's a sanitized version of something which happens all the time in real experiments. So it may look a little bit simplified, but that's because I simplified the problem just to make it easy to do calculations. But this is something that comes up in real experiments that involve randomization. So here's the problem. Again, it's not in the notes, so I'll try to write clearly up here. We have xi and yi. And xi is going to be a high-dimensional thing, so it's an r to the d. Yi is just going to be binary. D here you should think of as being like 10,000. So let me explain the setting. This really comes up when we're doing randomized trials, but we're going to simplify it a bit. The person comes in and I measure, let's say, 50,000 units on this person. So that's their x. So x is a very high-dimensional vector. Maybe genes aren't a good example. Something that I can measure fairly quickly, but it's very high-dimensional. The d is going to be much larger than the number of samples I'm going to get. Y is something of interest, like some protein they have in your blood or not. But let's imagine it's very difficult to measure. Either it's dangerous or it's expensive, so we don't want to measure all Y in every person. And all I'm interested in is what looks very innocuous and simple, which is the probability that Y equals 1, or same thing as the expected value. Okay, so what fraction of people have this protein in their blood, let's say? So again, one thing I can do is just take a random sample of people, measure the Y, and think, yeah, we'd be done. But again, we don't want to measure this on every person. And again, if you think back to where this really comes from, which is randomized trials, you randomize people to certain groups in order to see what happens to them on one group, not what would happen in the other group. So this is kind of a simplified version. All right, so that's fine. So I'm not going to measure Y in every person. So let's have a variable Y, which is 1 or 0, if Y is observed, and 0 if it's not. Okay. And the thing is this, I'm going to decide who to measure Y on or not. I'm going to look at their x values and construct, I'm going to randomly decide whether or not to observe your Y. And the probability that I observe your Y is under my control, but I'm going to let it depend on the x's. Maybe certain gene configurations I'm not interested as much in measuring the Y or whatever. So there's going to be a probability, let's call it phi of x, which is the probability that we take the measurement of your Y value given your x. The important thing is, so this is actually a function, right? It's a function of x. This is, again, like in a randomized study. Often when you assign people to treatments, you might look at the covariates first and decide what to randomize them to. So it's similar to that. But this is known. We know this. We are constructing this, okay? And I'm going to make one assumption about it. We're going to insist that everybody has to have some non-zero probability of being Y. Since we're constructing pi, we can insist that that happens. All right. However, of course, pi, the probability I measure your Y doesn't depend on Y because I obviously haven't seen your Y yet. So if I were to draw, for those of you who are familiar with directed graphs, I'm going to draw a graph here just to show you what's going on. If you're not familiar with directed graphs, this will still make sense anyway, which is simply that the probability of R depends on X, and the probability of Y also depends on X. Right? The probability you have this protein could depend on your genes, whatever these x's are. But the important thing is, conditional of x, these are independent. These are conditionally independent. This obviously doesn't depend on this for fixed x. All right. Let me introduce one more function, which is called u of x, which is simply the mean of x, mean of y given x. This is unknown. This is the probability you have this protein as a function of your genes. We don't know what that is. It's some unknown function. And that's the setup. All right, so just imagine people coming into your clinic, you measure the x, and you plug x in here, and you flip a coin with the probability pi of x. If it's heads, you measure the y. If it's tails, you don't get to see it. And we just want to estimate the mean of y. And you can't just use the mean of the observed y's. That's going to be biased. Right? This should be fresh in your mind from like election polls a week ago. How hard it is to account for biases and have selected data. And so we can't just ignore the fact that there's some sort of selection taking place here. But in this case, again, we've done the selection. This is also called a missing data problem, where we observe some of the data, but not all of the data. Some of the y's are missing. And again, what I want to estimate is this. Let me rewrite this another way. That's going to be helpful. We want to estimate the mean of y. I can do the law of total probability. That's the mean y and x integrated over x. By definition, I call that mu. So that's really mu of x, mu of x dx. And just to keep the calculation simple, because this is not critical, is x has some marginal distribution. It turns out it doesn't matter what that is for this problem. So let's just make life simple and take it to be, say, uniform on the, let's just take xi, in fact, to be in the d-dimensional cube, and we'll take p of x just to be uniform. That's not very realistic, but it's not important in what the calculation, so we'll just simplify it a bit. Okay? So x is randomly selected from this. Remember, this is very high dimension. So actually, this simplifies even more than this is really the integral over the cube. All right, so that's the problem set. Let me just pause and make sure that the setup is clear. Oh, and then the data, of course, are going to be triples. Xi, Ri, Yi, except that, keep in mind that we don't always observe this Yi. We only observe it if R's missing data. Okay, any questions about the problem? How it's set up? Everybody's okay? So we just want to estimate y. All right, so let me tell you, there's a lot of estimators here, and the one I'm going to put down is the simplest frequentist estimator. It's not actually necessarily the best estimator, but it's very simple. So let's use that. It's called the Horowitz-Thompson estimator. It's just defined in the following way. We just take theta hat to be the average. And let's see, we take yi. So let's look at this. First of all, I'm taking the product, which is good because we don't observe y if Ri is 0. So I'm really only sort of summing up over the y that I've actually observed. But then all I'm doing is something I think that seems very intuitive and very natural, which is when I observe a y, I'm weighting it by what's the probability of observing that y. Okay, so it's just a weighted average. This is something, things like this are used all the time in polling, which is you try to correct for, if you've got more men than women in the poll, you might want to reweight the poll to make it more like the population, and that's basically what you're doing, you're just reweighting the observations.
Why are you dividing it rather than multiplying it?
Because, well, actually, this is exactly what makes it, the first thing I'm going to show you is this is unbiased, because we're dividing it. Let's work this out. So I claim, my first claim is that this is actually unbiased. And you'll see why we divide, because I'm going to work out the mean. The mean of this? Well, the mean of an average is just the mean of one of them, right? So this is the mean of y times r. Let's condition on x. Let's use the law of total, what do we call it? Law of iterated expectations, is that what it's called? Where we take the expected value y and r y of x given x, and then take the expected value over that. So that's the expected value of, well, this is a function of x, and we're conditioning on x, so I can bring that out. And so I have the expected value of y times r given x, but these are conditionally independent. Conditional on x, these two have nothing to do with each other. So this is actually the expected value of y given x times the expected value of r given x. And the expected value of y given x, we define that to be mu of x. The expected value of r given x is pi of x. So now you can see why we divide it through, because this is just the expected value of this, which, as we saw, is precisely there. So it's an unbiased estimator. It's also bounded, right? Because y can only be 0 or 1, r can only be 0 or 1. This is bounded away from delta. So in fact, you can see that this is between 0 and what? 1 over delta. So I have IID, bounded random variables. I can apply, say, Hoeffding's inequality, for example, and we get that the probability, this is bigger than epsilon, is less than or equal to e to the 2 minus 2. I think there's going to be a delta in there somewhere. And here, what we conclude is theta minus theta hat. So we've learned a number of things here, which is, first of all, this estimator is completely non-parametric. You know, we don't know this function. This thing is unknown, the function that relates y to x. In fact, it's a pretty difficult thing, right? This is a 10,000 dimensional unknown function. Somehow we didn't even need to put that in here. We've got an estimator. Didn't depend on mu of x. Actually, it doesn't depend on anything. So this is a completely non-parametric estimator. It's consistent. You can see that this is going to 0. In fact, it's going to 0 at this rate. We can actually get a confidence interval, right? I can set this equal to alpha and solve for epsilon. And so I could get a 95% confidence interval. So everything works out pretty easily.
Can you say what are those expectations over?
They're over what's random, which is x, r, and y. First, I condition on x, and then you take the expected value of whatever's left over. Whatever's
At
left.
x before you take the expectation to pi of x, right?
Well, the expected value given x is a function of x. Here? Here. This is over everything that's random. X, r, and y. Whole joint. All right, any questions? So that's a pretty easy estimator. And again, these are the kinds of estimators. There's improved versions of this. These are basically the kinds of estimators that are often used in polling and sample surveys and so on. You can see, though, just to make a side comment, because I'm taking this to be known here, it's unbiased. If you have to guess pi, you get it wrong, bad things can happen. All right. Good. So now let's take let's see what the Bayes estimator is, or a Bayes estimator is. Well, for Bayesian inference, I need to take the likelihood times the prior. So what's the likelihood, first of all? Well, if we take let's write it like this. let's actually write out the joint density first. So P of x, r, and y. Write that as P of x, P of r given x, and P of y given x. Notice it's not y given x and r because, again, they're conditionally independent. Y and r are independent given x. Your genes, so your protein depends on your genes. It doesn't depend on whether I decided to observe it or not. That's what that's saying. And actually, we assumed this was 1. Just to make life simple. And now, let's think about what these are. These are actually Bernoullis, right? So the probability that your R is 1 is a Bernoulli, but the probability of success depends on x. So what's a Bernoulli look like? Well, it's mu of x to the r, and 1 minus, sorry, not mu, pi. Pi of x to the r, and 1 minus pi of x to the 1 minus r. Right? That's the usual Bernoulli thing. It's just that it happens to be a function of x. And y is the same. That's the one, the probability that y is either 1 or 0. That would be called that mu. Now there's one little detail we have to be careful of here, which is if we always observe y, that would be the Bernoulli likelihood. But if I don't observe y, that y is thrown out for that observation. So actually I need to do this. There's no contribution to the joint density from y if r is 0. We didn't see y. That's due to the missing, that we have this missing data situation. So the likelihood is the product of these terms. So there's our likelihood function of the problem. In fact, let's notice though that this is a known thing, right? This is just some number. We know pi of x. There's no parameters in it or anything like that, right? We've constructed pi of x ourselves. So these are just numbers. These are just, we can write that's proportional to. The only thing that's unknown in this whole problem actually is this function mu of x. That's the unknown parameter, so to speak. So that's this. In fact, if you want, you can write the likelihood, think of it as a likelihood for the function. Really, the parameter, in some sense, is the function mu. That's the main thing we don't know. And so, if you think about the parameter spaces, instead of all functions mu on the unit cubed, you should really think of that as the parameter space, and the likelihood function is defined in that parameter space. Everybody with me? Yeah.
Excuse me, I'm a little bit confused about the difference between R and Y.
R and Y?
Yeah.
Y is whether you have this protein in your blood. R is, I flipped a coin to decide whether to measure your Y or not. R is the outcome of that coin flip.
So R is modeling the absence or presence of the label.
Correct. Yeah, I flip a coin, the outcome is R, 1 or 0. If it's 1, I measure your protein. If it's 0, I don't measure the protein.
So your y and r is conditional independent, you ask.
Yes, exactly like that graph shows. So that's exactly right. Within, if you have two people with the same x, your y's and r's are independent. I'm only looking at your x to decide on r. I'm not looking at your y value. Any other questions? All right, now, what I have to do to do Bayesian inference is, here here I proceeded non-parametrically. I didn't make any models, so I want to proceed non-parametrically. Now, there's some technical stuff that we talked about with 702, which is how do you do Bayesian inference when the parameter space is some non-parametric class? Because I want to take mu of x, which is, what is mu of x, remember? It's the mean of y given x. X is a 5,000 or 50,000 dimensional covariate. Mu of x is a function which maps R to the D into probability. It's a very high dimensional function. I have to somehow put a prior over that class of functions and then compute the posterior. And that's actually possible. There are methods for doing non-parametric Bayesian inference. You put a prior on this class of functions, and you take the likelihood, you multiply by the prior, and you get the posterior. The details of this example are not so important. However, in this example, it turns out that the prior and the posterior are the same. There's no information in this likelihood function. Why is that? Well, because, let me try to show you this intuitively. Let's suppose for the moment that x is just one-dimensional. X is one-dimensional. Mu of x is some unknown function that we're trying to estimate. Well, we did talk about something similar, which was density estimation. This is not a density. This is a regression function. But there are ways to estimate a function non-parametrically. And we did like kernel density estimation. There's a similar thing for estimating a conditional mean. And again, there's a Bayesian version. You would put a prior on the set of smooth functions here. You would do Bayes' theorem, and you'd get a posterior over the set of functions. The problem is in 5,000 dimensions, the data are so far apart that there's essentially no data. You need the number of data points you need to estimate a function, even parametrically, let alone non-parametrically. It goes up exponentially with the dimension. So you need more data points than there are stars in the universe to estimate a 5,000 dimensional function. It's basically an impossible problem. Even estimating a 5-dimensional function is very difficult. Estimating a 50,000 dimensional function, it's virtually impossible. The way to think about that again is think about even on the real line, but imagine that the observations are really, really, really far apart. And what the likelihood is telling you about is something about the function at these observed values. You see, the function only enters the likelihood at the observed values. We're not really learning anything about the function in between. And you can kind of fill that information in using smoothness assumptions in 1 or 2 dimensions, but in 5,000 dimensions, again, the points are so far apart, it's pretty much impossible. So there's no information in the likelihood function about what's happening to the function. Since there's no information in the likelihood function, you can think of the likelihood as being flat over the space. What ends up happening is that the posterior distribution for mu is basically equal to the prior distribution for mu. And once I have my posterior for mu, that gives me a posterior distribution for theta. Why? Because theta is a function of mu. Once I have a posterior for mu, that because theta is a function of mu, you can think of it as some function of mu, that determines a distribution of theta. So in principle, I have a posterior distribution for mu, and therefore I have a posterior distribution for theta. But as we've just seen, posterior is basically, well, it's the same as the prior. We haven't learned anything from the data. So it can't possibly be consistent. What do we mean by consistent? In Bayesian inference, by consistency, we mean that the posterior distribution should converge around the true value. We'll talk about that in a minute. But that can't possibly be happening here because it's not changing as you get more and more data. So this is actually a theorem, but it's a little bit hard to state, so I'm just saying it intuitively, which is that the Bayes estimator here is inconsistent. It doesn't concentrate around the truth. In fact, something much more subtle is happening. Notice that anything that only uses the likelihood function, which is what Bayesian inference does, involves these mu's. Here's a question. Where's the pause? Notice that our estimator over here is a function of these pi's. But you can see that the Bayesian posterior cannot be a function of the pi's. Why? Because pi's are constants. And by the mechanics of Bayes' rule, anything that's a constant that doesn't involve a parameter just drops out of the posterior. So it's a fact that the posterior is not a function of pi. We skip this in this course. We say that the pi's are ancillary. They're statistics that don't involve parameters. So these are ancillary statistics. It just means they fall out of the posterior distribution. They're not there. They don't appear anywhere in the posterior. They can't appear in the Bayes estimator. And in fact, so this theorem, I should say this theorem I'm talking about is due to Ritchoff Robbins, if you want to look for the paper. The theorem says that any estimator, never mind the Bayes estimator, any estimator that is not a function of the pi's cannot be consistent. It actually says that it converges arbitrarily slowly, which is, when d is large, that's what it's saying it can't be consistent. So we have this interesting difference again between the Bayes estimator and the frequentist estimator, which is that the Bayes estimator doesn't involve pi, but if any estimator doesn't involve pi, it cannot be a consistent estimator. Whereas this estimator, this Horowitz-Thompson estimator, is clearly a function of the pi's, and it has very simple behavior. Yeah.
Just you need exponentially more samples. You say that it's impossible. So again, if you take the limit of the sample going to infinity, you should be able to have a posterior that converges to the point.
So what happens is, if you keep t fixed and you let n go to infinity, you would actually get a consistent answer, but it converges at logarithmic rate. So it's very, very slow. But more importantly, keeping d fixed and letting n go to infinity is very artificial because it doesn't capture the finite sample situation that d is bigger than n. So formally, if you're going to let n get bigger, you also have to let d get bigger. And if you do that, you won't get consistency. So this is something that comes up in real life because when we do randomized experiments, there's a question of should your estimators depend on the randomization probabilities? And we see that in the frequentist answer, it very definitely does depend on the randomization probabilities. From the Bayesian point of view, this is a general fact. The Bayes estimator doesn't depend on the randomization probabilities. And so there's a lot of controversy about that issue. Is should they or should they not depend on the randomization probabilities? Kind of a deep philosophical question, I guess. But from our point of view, it's just, again, they're two different things. There's two different goals. The estimators are very different. I picked these examples because they are examples that show you that they can be different. I just want you to be aware that there are situations where the Bayes and frequentists can be different. But they're not always different, and I want to show you now cases where they're very close. Before I do that, though, let me see if there's any questions. Yeah?
So I guess one thing I'm having trouble grasping is what it means for my Bayes estimation process to be successful, because we have like frequentist notions of if I have a frequentist confidence interval, a 95% confidence interval, and it covers the true parameter in the future for future data, 95% of the time we were successful. So what does it mean to be successful in a Bayes setting?
That's a really good question. What does it mean for a Bayesian analysis to be successful? And you'll get different answers to that question. So some people do Bayesian inference, but they actually put on a frequentist hat and say, in the end, though, I'd like my Bayes method to still have good frequentist properties. So for example, I'd like the posterior distribution to concentrate around the true value at a certain rate. So that's now taking sort of stepping outside the Bayesian framework and taking a frequentist look at the Bayesian procedures. You'll see some people do that. There are other people who would say, I'll call them Bayesian purists, for lack of a better term, who say that's irrelevant, that for it to be successful, if I've stated my prior, and that's what I truly believe, and I've stated my x given theta, and that's what I truly, you're successful. That doesn't matter what the properties of it are. I followed the Bayesian description. I computed the posterior. That's a correct description of my beliefs. I've succeeded. And they would say that the frequentist properties, like consistency, are irrelevant. They say that's not the goal of what they're doing. So you get very different answers. That's why you can see, you know, I'm always leery about talking about this stuff because it's sort of, we're leaving, you know, theorems and stuff like that and getting into what are really philosophical issues. And so I always mention all this stuff with a bit of trepidation because there's a lot of different opinions and so on here. All right. Any other questions? All right. So now we've seen examples that show you most definitely there are cases where the Bayesian answers and the frequent answers are just going to disagree. But there are cases when they're going to give very similar answers, and we can talk about that now. And that's especially in the cases we talked about earlier in the year when we did parametric inference, when we had parametric models. And we had all those regularity conditions and so on. In that case, and especially if the dimension of the parameter space is fixed and we get more and more data, in that case, it turns out the posterior distribution and the frequentist kind of analysis are typically going to be very similar. And I alluded to that a little bit earlier, but let's just look at that a bit more carefully. There's something called the Bayesian central limit theorem that says if you have a parametric model, so I'll write it like this now, P of x given theta, theta is some subset, where V is fixed now. Okay, it's just like three-dimensional, like a normal model, say, something like that. And remember, there's regularity conditions. We have to assume, of course, that it will always be for these sorts of things. Then I'll just state the Bayesian central limit theorem informally, which says that the posterior probability of theta given x1 xn can be approximated by a normal, and the mean will be approximately the MLE. And the variance will be the Fisher information. So what that means is that if I compute like a 95% Bayesian interval, it's going to be theta hat plus or minus z alpha over 2, which is precisely what? That's the wall interval. So what that's saying is that the Bayesian 95% posterior region is going to be asymptotically the same as the walled confidence interval. So in that case, there's clearly, whether you want to use the Bayesian approach or the frequency approach doesn't matter so much because you're going to get approximately the same answer. And let me just outline why that's true. So we write down we'll do this fairly heuristically. We won't do it with the same detail we did the MLE. The log posterior is the log likelihood, so that's the log plus the log of the prior plus another constant, because don't forget that the posterior is the likelihood times the prior divided by some constant. Just to make it integrate to 1. Actually, I call that in the notes log, so it doesn't matter. And the first thing to notice is that this is the sum of n terms. I mentioned this before. This is n things rounding up. This is a single number, and this is a single thing. So actually, the dominant term is this first term. It keeps accumulating. So you can show that this is approximately equal to this first term, which is really what it's just the log likelihood up to a constant. Actually, let's leave out the constant, so we can always normalize things later. So the key here is that to a first approximation, and actually this is a fairly accurate approximation, prior doesn't matter much. There's n terms here. This term only affects things up to order 1 over n. That's the effect of this term, because it's one number, and this is summing up n things. So the prior, asymptotically at least, doesn't have much effect. And so we have that this is approximately equal to the log likelihood. Now we just do a Taylor series approximation. It's very similar to the proof that the MLE is asymptotically normal, but not quite, because don't forget we're thinking of theta as a random variable. So if we just expand the log likelihood, it's equal to the log likelihood theta hat plus the first term is the derivative of the log theta, that's 0. So all we're left with next is the second term here, theta hat minus theta squared over 2 L double prime. And then smaller order terms, so I'll just write this as approximately. And so the posterior, therefore, is proportional to, if I exponentiate all this. Now, remember, from the posterior's point of view, anything involving the x's is constant. It's the theta that's random. So in particular, this is a constant. So I can put that into the proportionality constant and write this way. It's the theta that's the random variable here. And if I just multiply by negative, well, we know that this is the sum of the second derivative, which will be approximately to the Fisher information. So this is or in other words, actually, when I write it this way, I could call that sigma squared or sigma squared. And that's it. So it's quite simple. And of course, that's just the one-dimensional version. So what we conclude is that the posterior is approximately normal, centered at the MLE. The variance is approximately 1 over the Fisher information. And so, therefore, the posterior intervals and the walled intervals will be approximately the same. And that's an example where they're going to be very similar. Yeah.
So what we did is we ignored the prior term and saying that the maximum of the posterior would happen at the same point that the molecular's maximum happens.
Up to order 1 over n. So the truth is, let me clarify that. The maximum of the posterior, let's call that theta triple, is not actually the theta hat, the MLE. It's equal to theta hat plus order 1 over n. That error comes from ignoring this term. But because, again, this is based on n terms and this is based on 1, this has sort of 1/n of the effect. And so that's why it's only a small, very small difference, actually. Yeah, this is very, very hand-wavy. Okay, we could prove this more rigorously like we did, say, the maximum likelihood normality. But I don't think it's worth going into the details. I just wanted to give you some intuition about why this is true. So the conclusion is that in finite dimensional parametric models with lots of data and the standard regularity conditions, there we expect the Bayesian and the frequentist approaches to be very similar differences. And so now we've seen there are cases where they're going to be similar, there are going to be cases where they're going to be different. Typically the differences come about when we're dealing either with high dimensional problems or non-parametric problems. That's when you start to see the differences, is high dimensional or non-parametric. But for finite dimensional parametric problems, there really isn't, generally speaking, so much difference. I mean, I'm sure there's exceptions, but generally speaking, that's the case. Okay, any questions? Okay, good. So, there's only 2 other things I wanted to say about, maybe 3 other things I want to say about Bayesian difference. One of them I already mentioned, which is it's a really interesting topic, which is how do you compute posterior. As I mentioned in the last class, in practice, one often has to resort to Markov chain Monte Carlo. That's a very, very big topic. There are whole courses on MCMC methods. Second thing is, section 7 is optional. You can look at that as well. There's a Bayesian approach to hypothesis testing, where you can put a prior distribution on theta that includes sort of a discrete piece of math at the null hypothesis. That's sometimes what people do Bayesian hypothesis testing. So you can do very similar calculations. You can compute the posterior probability that the null hypothesis is true. And so that's all done for you in section 7. But I don't think we need to go through the details. But it's there if you want to look at it. And the other thing is that I mentioned briefly in that other example is there is a whole large effort going on about doing Bayesian inference in non-parametric cases, which is much more complicated. Both the theory is more complicated, the computation gets more complicated, and typically that's cases again where you do get disagreements between the Bayesian and the frequentist approaches. So it's quite interesting. And sometimes we do 1 or 2 lectures on that, 7 or 2, depending on if people are interested in that. So if you want to know more about that, those of you at 702, we can talk about it in that class. That's pretty much all I wanted to say about Bayesian inference. Are there any questions? Okay. Let's move on. The next topic is prediction. And this is sort of scattered a bit through the book. Some of this is chapter 13, some of this in chapter 20, some of this in chapter 22. If I was writing the book again, I would probably organize it differently, but that's the way it is. Those of you who are taking 701, 10701, of course, have seen quite a bit of prediction, but I'm not going to assume, not everybody's taking 701, so I won't assume you've seen it, but prediction is obviously, these days, a really important problem. What do I mean by prediction? We're going to have data, Z1 to Zn. The data come in pairs, and X is called different names. In ML, people tend to call it features. In statistics, we tend to call it the covariate. There's other names too. This will be, say, in RD. Y is the response of the outcome. And there's many different possibilities here, but the two most common ones, the ones we'll talk about, are if Y is real value or Y is binary. And of course, the goal is I get n data points. So statistics is called the data set, and then machine learning is called the training data. I'll keep trying to translate into world. And now along comes a new X, and of course we want to predict Y. And the purpose of the training data is to help us construct a good predictor. So in this case, people usually call this regression. And in this case, we usually call it either classification or discrimination or pattern recognition, depending on your background. And of course, this could be discrete. It doesn't have to be 0, 1. We'll just do the 0, 1 case. Since I'm talking about the similarities and differences between machine learning and statistics, I guess this is one of them right here, which is, I think in a typical statistics course like this one, you see that there's a lot of topics, and then one of them will be prediction. So statisticians tend to do predictions like one corner of statistics. Whereas I think in machine learning it's the opposite. I think the problem is prediction. And all that statistical stuff, well, that's just some little corner over here. So depending on, your point of view, what the relationship is between prediction and more general statistical inference, I guess, can vary. But at any rate, it's certainly a common and important problem. And these days, what makes it all very interesting is we're often very interested in X's being complicated objects like images and so on, and possibly very high-dimensional objects. All right, so the goal is what? Well, is to predict well. So we're not really estimating a parameter, at least not directly. We're sort of implicitly estimating a parameter, but it's sort of implicit. We're really just trying to predict well. And so what does that mean? Well, in regression, we're going to somehow come up with a function that I call m here, g of m. Let's say g of x, following x. And of course, this came up precisely in the problem we just did a minute ago, which is what I call mu of x. This is going to be what I'm using to predict the future. And so along comes a new guy. There's his x. I make his prediction. And now, the nice thing about prediction that I like is that the question of what does it mean to be successful is much clearer. Because I can just say, well, I want my prediction to be close to the true value of y. There's different loss functions we can use. The most common loss function would be squared error loss, but of course you don't have to use squared error loss, but that's the most commonly used one. So that would be a measure of success here, is to make that prediction error, the expected prediction error, small. The one many of you are familiar with in classification would be, you've got to come up now with a, remember to watch the time. I'm going to stop in a minute so I can get back to homework. In that case, of course, what we're coming up with is a function h, but this can only take values 0 or 1. I have to predict, is it spam, is it real, is it this, is it that? And again, there's a number of different loss functions we can use, but the most common risk would be the probability that y is not equal to the predicted value. Okay, so what we'll talk about then on Friday is we'll go through these prediction notes. Then remember, no classes next week. And I will now give back homework. Any questions before we break?
Yeah, no, I see. I'm pretty sure you can, but
but there's probably artificial intelligence Bayesian networks, which I think uses, if not the exact Bayesian inference, it uses a Bayesian interpretation of statistics. So you have, like Director Grassi is talking about, where things that influence something else, or something that means something, X influences Y, or Y is influenced by X. You're trying to figure out the probabilities in order to predict it later. You populate your base data with like probabilities over each variable that reflect your beliefs. They don't necessarily reflect. Our beliefs can come from a frequentist thing. Like if you're looking at the probability of rainfall, which is a frequent event, then your beliefs may correspond with frequent stuff, but it's a little different. Because then there might be infrequent events for which you don't have a probability, like a frequentist one, and then you like propagate those. You like update your beliefs based on.
Yeah, so that's another thing I have. Another question I have is like, how can you do phasing without people
I'm in a rush, I think.
like, it seems to me that it just comes out.
So I don't think Bayesian people ignore data necessarily, right? Like, it's just that they, I think, are a little bit more advanced. I think it's the difference between like deduction and induction. I think it's a very similar philosophical.
No, that makes sense. Actually,
You're not joining us?
what's that?
You're not joining us? This is it. No, Joel.
Well, if they're just doing just the way.
So last time I used to call it, like you said, like a file just didn't make it in last time. Right? You can't bring it back to